Okay, it looks like we've hit 1 minute after the hour. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program, and it's co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, if you're not intending to speak, please just make sure your microphone is muted and your video camera is off. I'm going to go ahead and turn it over to Lisa to introduce today's speaker. Thank you, Lisa.
Thanks. So for those of you who I haven't had a chance to meet yet, my name is Lisa Luna. I'm a new Mendenhall postdoc here at the USGS in the Landslide Hazards Program. And it's a real pleasure to welcome a dear colleague of mine from the Potsdam Institute of Climate Impact Research, Sara Vallejo-Bernal. Sara is originally from Colombia, where she completed her bachelor's degree in civil engineering and her master's degree in applied mathematics at the National University of Colombia. But since 2020, she's been based in Germany and has been working on her PhD at the Potsdam Institute for Climate Impact Research. Her research interests are in atmospheric complexity, in land-atmosphere interactions, and in natural hazards. And during her PhD, she's been investigating the dynamics and impacts of atmospheric rivers using a complexity science approach. So in particular, she uses tools like probability theory, nonlinear time series analysis, and climate networks to investigate the spatial and temporal patterns of heavy precipitation events triggered by atmospheric rivers, and in particular, their relation to natural hazards. Today, Sara is going to be telling us about some work that she did as part of her PhD, looking at atmospheric rivers and landslides, and the title of her talk is Atmospheric Rivers Cause the Majority of Precipitation-Induced Landslides in Western North America. So thank you very much for joining us, Sara, also late at night in Potsdam, and I'll hand over to you. We're looking forward to your talk.
Thanks a lot, Lisa, for the kind introduction. It is my pleasure to be here today. And before I start, I want to tell you that I'm a tropical human going through extratropical winter. Therefore, my voice is not in the best condition, but I'm really happy to be here. So sometimes I will take some water, make some passes, just for you to know. And before jumping into the topic, I really want to thank my co-authors. One of these co-authors is actually Lisa, for all their valuable contributions. Okay, so as a quick overview of my talk, I'm going to start with an introduction to atmospheric rivers. Then I'm going to talk about the role of these atmospheric features into precipitation. And then I'm going to tell you how are atmospheric rivers and precipitation related to landslides. So last week, as I was preparing my slides, a monster storm was wreaking havoc in California. It was causing extreme precipitation and winds, and the media got flooded with this kind of headlines. California flooding, how atmospheric rivers led to a state of emergency. Los Angeles hit by mudslides, flooding as atmospheric river persists. 9 dead, hundreds of landslides reported in wake of atmospheric river that slammed California. And there is a common term to all these headlines, and it is atmospheric river. But what is an atmospheric river? So I'm going to use this amazing animation by Scott Duncan, where he shows precipitable water to explain that an atmospheric river is a long, narrow, transient corridor of intense moisture transport in the lower atmosphere. Atmospheric rivers are responsible for transporting the water, the moisture from the tropics to the mid-latitudes. In total, they account for 90% of the poleward moisture transport, and therefore they play a critical role in the global water cycle. And to give you a sense of their magnitude, on average, an atmospheric river transports double the Amazon of the Amazon, double the flow of the Amazon River, and therefore our atmospheric rivers are the largest rivers on Earth. So they are essential for the freshwater supply of the mid-latitudes. For example, it was found that from 1950 to 2010, atmospheric rivers broke up to 74% of US West Coast droughts, but they are also responsible for natural disasters. For instance, from 1978 to 2017, atmospheric rivers accounted for 84% of flood losses in Western United States. So this brings me to our first motivation, and is that Western North America is a hotspot of landslide and atmospheric river activity. And this slide might be familiar to many of you. Here I'm showing the map of known landslide occurrence across the conterminous United States. These little dots in colors indicate a confidence metric for the occurrence of the landslide, and the gray shading is indicating the USGS landslide overview map. And there is something important here, and is that not only Western North America is a hotspot of landslide activity, but it's also a region where the confidence of the landslides that we have reported is really high. So basically, we know where landslides are occurring. And then from the atmospheric perspective, I'm going to use this animation. But before playing the animation, I want you to notice that the gray shading is indicating the moisture transport in the atmosphere, and each contour and colored region is showing you an atmospheric river that is active at the moment. And of course, I would like to draw your attention to what's going on in the western coast of North America, and especially to the sequences of atmospheric rivers that are happening one after the other, and are all of them hitting the western coast. These kind of sequences are known as atmospheric river families. And then some key factors about atmospheric rivers. Their lifetime, it's on average 79 hours, and this time accounts for like the moment when the atmospheric river originates, all the time the atmospheric river is traveling until the atmospheric river dies. Then on average, they can travel for 3,300 kilometers. Their average width is 850 kilometers, and their average length is 3,000 kilometers. And as you saw in the animation, at any given time, depending on the season and also on the location, there are on average between 11 to 17 atmospheric rivers active on Earth at any time. And also to better explain the physical processes behind the atmospheric rivers, I'm using this nice sketch. So as I told you, atmospheric rivers transport warm, moisture air from the tropics. Then these atmospheric rivers get to the mid-latitudes, where they can, for example, meet the topography. Then this topography makes the moisture air, forces the moisture air to rise. And when this moist air rises, then the moisture condenses, the water vapor cools down, and this produces the precipitation in forms of rainfall, but also snow. And depending on the intensity and the persistence of these atmospheric rivers at a given location, the impacts, or let's say the consequences, can be different. Atmospheric rivers have a dual behavior, and this motivated the development of an atmospheric river scale in 2019. This scale has 5 levels. Levels 1 and 2 are mostly beneficial atmospheric rivers. Then level 3 describes atmospheric rivers that have a balance of beneficial and hazardous. And finally, levels 4 and 5 are for mostly hazardous atmospheric rivers. So now we move on to the second motivation of our study, and it's the role that atmospheric rivers have on the precipitation regime in Western North America. And I would like to start mentioning the overall contribution of atmospheric rivers to the total annual precipitation. Shown in this plot is the fraction of the total annual precipitation that is related to atmospheric rivers. And we can see that there is a clear spatial pattern. First, from south to north, this contribution increases and is especially important for Northern California, where it reaches up to 70% of the total annual precipitation. In some other areas, this value is at least 30% along the western coast. And then if we move from the west to the east, this contribution starts to decrease. Then if we look into the seasonality of this contribution of atmospheric rivers, as expected, they contribute more during the extended winter from October to March, but they still make contributions during the summer. And now, okay, we know the contribution of atmospheric rivers, but it's not the same to have a steady precipitation regime than to have an intermittent precipitation regime. So it is also important to understand the frequency of precipitation in these locations. And here, what I'm showing is the number of days necessary to accumulate 50% of total annual precipitation. These pink and orange colors are for regions where you need less than 10 days. And then blue and black colors are for regions where you need more days. And again, there is a really clear spatial pattern. We need less days to the south. We need more days to the north. This means that precipitation is less frequent here in the south of Western North America and is more common here in the north. And if we analyze the contribution of atmospheric rivers in terms of intensity, so how strong are the precipitation events that happen during atmospheric river conditions, what we're seeing here is the contribution of atmospheric rivers to the total annual precipitation, so same result that we have already seen. Also, basically the same values. But what's really important here is this part of the figure. This is showing you how big, how high is the intensity during atmospheric river episodes compared to the normals. And it reveals that atmospheric rivers deliver 2 to 3 more times precipitation than other atmospheric drivers. And then if we know that this is the precipitation regime of the last decades, but you can wonder, how is the precipitation regime expected to be in the near future? And this has also been addressed. Here we're showing the change in the contribution of atmospheric river precipitation to total precipitation. In this case, blue colors indicate that atmospheric rivers are going to contribute 20% more, up to 25% more of the total precipitation. This is especially true along the western coast of North America, and there is a shift towards the south. So precipitation from landfall in atmospheric rivers will be enhanced by climate change. But then you might be wondering, okay, I don't really understand, because precipitation is the frequency of precipitation is supposed to decrease. And what's going on here is that these precipitation events are extreme precipitation events, which will become more frequent and more intense. And this change in the precipitation regime is almost entirely due to atmospheric rivers. So we have scientific evidence that atmospheric rivers cause heavy precipitation when they hit the west coast of North America. But do they also cause heavy precipitation in the mainland? There were some exploratory studies about this regard, but in particular, I want to comment on the first outcome of my PhD project. We studied the delayed effects of atmospheric rivers on heavy precipitation. To do so, we use a time series of atmospheric rivers And we also consider time series of heavy precipitation, which we define as the 95th percentile of the daily precipitation intensity. And I'm not going to really dig into the details here. I just want to mention that we use some tools from the complexity science. First tool is called event synchronization. This is a nonlinear temporal correlation measure. We also use climate networks, which are graph representations of complex systems. And by doing so, we were able to study the evolution of the synoptic conditions during atmospheric river events. And since we were considering nonlinear correlation measures, we were able to reveal new atmospheric patterns that occur during atmospheric rivers. So here I'm showing two main variables, water vapor transport and precipitation. We were able to evaluate different temporal delays. First time window is from 0 to 3 days. It is the time when the atmospheric rivers are hitting the western coast of North America. And what I'm showing here are anomalies for the two variables. Red colors indicate that the value of the climatological variable was higher than the normals. And as you can see here, we found very intense moisture transport from the Pacific to the western coast of North America, which is confirmatory of the presence of atmospheric rivers. This intense moisture transport was then reflected in intense precipitation at the western coast of North America. But if we then use our nonlinear correlation and we extend the time window from 3 to 12 days, we were able to find a really nice synoptic pattern. And there are like some particular atmospheric rivers with some particular atmospheric configurations that occur mostly during the summer that are able to penetrate the continent. They can transport this moisture from the Pacific to the northern part of North America. They can reach Canada, and then they can cause heavy precipitation events there. So we were able to show that inland penetrating atmospheric rivers can organize heavy precipitation over large regions, and that their effects are not localized or restricted to the place where they make landfall. And then we have arrived to the third motivation of our work, and is this intuition that we have that atmospheric rivers cause precipitation-induced disasters, in particular in Western North America. And this is like not only intuition, this is what we experience. So in this regard, there are some nice studies. The first one related atmospheric rivers and avalanche fatalities in the Western United States. And in this study, the authors were able to find that between 1998 and 2014, atmospheric rivers conditions preceded 31% of Western United States avalanche fatalities. This is the overall rate, but if we look at some, like for example here, the Pacific Northwest, we see that this percentage can reach up to 75% of the fatalities. Then, then the role of atmospheric rivers in floods, and in particular flood losses in the Western United States, was also assessed in 2019. And what I'm showing here is the proportion of insured losses due to atmospheric rivers. There is, again, a really nice spatial pattern. There are slightly more losses in the north than in the south. And if we move from the west to the east, the insured losses starts to increase, like the insured losses attributable to the atmospheric rivers. The authors were able to show that atmospheric rivers are the primary drivers of flood damages in the Western United States. Overall, from 1978 to 2017, atmospheric rivers accounted for 84% of all insured flood losses. And then they were also able to demonstrate that flood damages increase exponentially with atmospheric river intensity and duration. So the stronger the atmospheric river, the more catastrophic it is. And now we finally jump into our topic. In 2016, there was like this really nice study analyzing landslides in West Coast metropolitan areas. The objective of the authors here was to investigate what weather triggers landslides along the West Coast. They used 9 years of landslide data, and then they were able to find relevant relationships between landslides and rainfall events. But what's even more interesting for me and for my team, and I really hope for you too, is that at Puget Sound, they were able to identify clear atmospheric river conditions, leading to these extreme precipitation events that then trigger landslides. And here I want to stop in this quote from the paper, because I really consider that during this study, the authors start paving the way to our study, and they wrote that the assessment of future changes in landslide hazard for the entire West Coast requires consideration of future changes in the occurrence and intensity of atmospheric rivers, in their duration and clustering, and I guess by clustering we're referring to atmospheric river families, and in the occurrence of short duration sub-daily extreme rainfall as well. So after that study in 2018, there was like this super nice study about atmospheric rivers and shallow landslides in California. Here, the authors use landslide data, precipitation data, and also atmospheric river conditions. And what they are showing here is the number of heavy precipitation events that were exceeding the precipitation thresholds that trigger landslides. And then the coloring is showing you the percentage of events that were simultaneous to atmospheric river conditions. So like this pink color means that basically all of them were simultaneous to atmospheric river conditions. And then the authors concluded that from 1995 to 2015, atmospheric rivers coincided with 60 to 90% of rainfall events, exceeding precipitation thresholds and triggering shallow landslides. Then our very specialized study followed, where the authors studied widespread reactivation of landslides in the Northern California coast ranges. These black polygons are the landslides that they studied, and the shading is showing the precipitation intensity. And then they concluded that extreme rainfall during 2017 resulted from an unusually high number of atmospheric river storms. And finally, there was also super nice study in the San Francisco Bay Area. In this case, the authors had an exceptional data set of landslides that occurred during 142 years. And they found that from 1871 to 2012, 82% of landslides in the San Francisco Bay Area coincided with atmospheric river conditions over the near offshore Northeast Pacific. So we learned a lot from all these previous studies, but we were also able to identify some research gaps and some challenges that the authors were facing. First challenge is related to the data. Some data is really localized, so they were able to perform case studies or like regional studies. Some other data was very short, so they were able to analyze just 9 years. And then, due to these limitations, a theoretical framework to attribute and quantify the causal relation between landslides and atmospheric rivers is still lacking. And in particular, there are some open questions. How can we consider the uncertainties of the input data, because our data is highly uncertain? How can we assess the statistical significance of the findings? And then, do families of atmospheric rivers cause landslides more frequently than individual events? Because this is something that the intuition might suggest. And lastly, do weak atmospheric rivers also cause landslides? So at this point of my presentation, and before diving into our results, I would like to convey these first take-home messages. The first one is that on average, about 40% of annual precipitation in the West Coast states occurs in just a few atmospheric river events. Atmospheric rivers are the main drivers of extreme precipitation in the West Coast. Some atmospheric rivers can penetrate the continent and cause extreme precipitation over the mainland. And atmospheric rivers are therefore closely related to both water supply and precipitation-induced disasters in Western North America. And lastly, I would like you to especially remember that an atmospheric river family is a sequence of atmospheric rivers hitting the West Coast in close succession. So now let's dive into the topic and let's talk about our study that related atmospheric rivers and precipitation-induced landslides in Western North America. So our main research question was, can we prove and quantify the strength, directionality, and significance of the causal relation between landslides and atmospheric rivers in Western North America? And to do so, we propose a two-step approach. In our first step, we are going to attribute rainfall, or also snow, to landfalling atmospheric rivers. And then we are going to use nonlinear dynamics to relate landslides to this atmospheric river related precipitation. So as input data, we use the COR1 catalog of atmospheric rivers, which make landfall along the western coast of North America. These atmospheric rivers are identified over these coastal grid cells, and this catalog covers a period from 1948 to 2018. It has a 2.5 degree spatial resolution, 6 hourly temporal resolution, and here I'm showing you the frequency of atmospheric river conditions at each grid cell along the coast. And there is a really clear spatial pattern. Atmospheric rivers are more frequent to the north than to the south. And if you look at the color of the rings, light colors indicate weak atmospheric rivers, and as expected, weak atmospheric rivers are the more common ones. We also employed precipitation data from the Persian product, and what I'm showing here is the proportion of wet days over Western North America. There is we found like the expected pattern, less wet days to the south, more wet days to the north. But we also think, but we're also showing the contour, the topographic contour line, and it's really interesting that the let's say effect of the orography is already visible in this proportion of wet days. And then on the right-hand side, we have the mean precipitation intensity during these wet days. And I expected this precipitation is stronger along the coast and then is weaker over the mainland. Again, reflecting not only the frequency of atmospheric rivers, but also the role of the topography. Lastly, from the side of the landslides, we use three landslide inventories, the landslide inventories across the United States version 2. We augmented this inventory with the Washington landslide compilation, and we updated our data with a more recent version of the NASA Global Landslide Catalog. From all these data, we extracted the landslides that were occurring in our region of interest, and we also only consider the landslides for which the day of occurrence was reported. After doing this, we ended up with 13,488 precipitation-induced landslide observations. And in particular, we decided to study the occurrence of landslides instead of the number of landslides that occur. So we are basically interested in the event, was there a landslide, at least one landslide or no? And therefore, we define a landslide day as a day with at least one precipitation-induced landslide reported in our data. If we take a look into the temporal evolution of our data, here I'm showing you a time series of landslide days in the left-hand side and precipitation-induced landslides in the right axis. And there is also a clear pattern. More landslides have been reported recently, and this might be really related to the date when the NASA catalog came out to the public. And finally, we also wanted to make sure that the landslides we were considering were precipitation-induced landslides. And therefore, here I'm showing you the time difference between the landslide day and the previous wet day, a day with a precipitation intensity greater than 1 millimeter. And what we found is that basically more than 90% of our landslides were simultaneous to precipitation events, and those that were not simultaneous occur after 2 days of the precipitation. So if we compare this pattern to the landslide susceptibility map of the conterminous United States, we see that there is a clear, that this data is clearly following this pattern, but it is also showing that more landslides are reported close to main cities, metropolitan areas, and densely populated locations. And then we took all our landslides and we decided to bin them into a 2.5 degree resolution grid. And in particular, this grid matches the grids of the atmospheric river catalog along the West Coast. And then we calculated the fraction of landslide days at each location. We found this, again, really nice spatial pattern, which is everywhere. More landslides occur, or at least more landslides are reported to the north. And also this frequency is higher along the coast and is lower over the mainland. And in particular, the highest landslide probabilities are observed around Seattle and Portland. So we wanted our methodological approach to take into account the physical processes that link atmospheric rivers to landslides. And to do so, we decided to do some case studies first, and I'm going to show you 2 really nice examples. The first example is a single atmospheric river. To understand this figure, you need to read it like from the right to the left. So this is the day of the landslide. Landslides were reported in December 3, 2007. And here, like in the first row, I'm showing moisture transport. In the second row, I'm showing precipitation intensity. And finally, in the last row, I'm showing you the temporal evolution of the hourly precipitation. So the blue line is showing hourly intensity, and the red line is showing you the total precipitation, the accumulated precipitation. And lastly, this gray shading is indicating the presence of an atmospheric river along the western coast of North America. So if we consider the day when the landslides were reported, and we analyze 10 days in advance, we see that there were some tiny precipitation events, but when you look at the atmosphere during those days, there wasn't, an atmospheric river was not there. And then suddenly, during the landslides, you have this extreme atmospheric river. This was extreme atmospheric river indeed, which is transporting like an incredible amount of moisture to Washington and Oregon. And then this caused really extreme precipitation, which triggered thousands of landslides. And if we compare these to case study 2, then like we will find some difference, because this time we are going to explain, or I'm going to explain you an atmospheric river family. So like same configuration of the figure, but now you can see that there are more gray regions here in the time series. So already 10 days before the landslides, there were atmospheric river conditions at the landslide locations. And you might tell me like, okay, Sarah, but that doesn't really look like an atmospheric river. Just keep in mind that I'm using a nonlinear scale for the moisture transport, because this event here was, again, like quite extreme. So it's for visualization purposes. But like, I hope you believe me that there was an atmospheric river flowing here. This atmospheric river started to deliver precipitation to Oregon and Washington. Then some days after that, like actually 3 days after that, we still see some atmospheric activity, and atmospheric river conditions were still detected at this location. And it was raining in California, but okay, like not that much compared to the precipitation in Washington and Oregon. Precipitation starts to accumulate, and then a really intense atmospheric river comes into the picture. We have this really intense moisture transport here, and this resulted in really extreme precipitation in California. And then suddenly you have landslides occurring at more than 1,000 kilometers of distance. So what have we learned from this analysis? That we need to spatially attribute precipitation to atmospheric rivers, but we cannot do it based on the landfalling location of the atmospheric rivers or some distance criteria. And this was already hinted by the results of like all the results in California. Authors were commenting that to calculate the contribution, they were assuming that any atmospheric river will cause precipitation anywhere. And then in my first result, in like the one that analyzes inland penetrating atmospheric rivers, confirm that some atmospheric rivers may cause precipitation in really distant locations. So this distance criteria is not enough, and the landfalling location is also not the best proxy. So to overcome this, we propose a probabilistic attribution approach. This approach is going to be evaluated for each location of our study region. Let's consider, for example, this grid cell here. At this location, we have a time series of precipitation. These blue lines indicate the occurrence of precipitation events, and their height indicates the precipitation intensity. And then we have a time series of atmospheric rivers, and in this case, we consider the presence of or absence of an atmospheric river along the west coast of North America. We use the time series of atmospheric rivers to classify the precipitation into two categories: precipitation that occurred during atmospheric river conditions and precipitation that occurred during normal conditions. And then we take this time series of precipitation and we construct two attribution scenarios. The first scenario is for atmospheric river days. In this case, we calculate a probability distribution function for the precipitation intensity. And then we use the blue events and we calculate the second scenario, which is the probability distribution function during non-atmospheric river days. And then we consider a precipitation amount X. And we are going to evaluate the probability of this precipitation event under both scenarios. But since this measurement of precipitation might also be highly uncertain, we want to consider some deviation. And we decided to use the standard deviation of each distribution as an intuitive approximation to this uncertainty. So we take this standard deviation, we consider an interval around x, and we calculate the area under the curve. And this is basically the probability of having a precipitation intensity between this value and this value during atmospheric river days. We do the same for the non-atmospheric river days scenario. And since these distributions are different, then the standard deviation is also different, and the uncertainty of the precipitation measure under both scenarios is different. And we calculate again the area under the curve. We obtain this precipitation of having, this probability of having a precipitation event during non-atmospheric river days. And then we compare these two probabilities, and we establish an attribution condition, which says that the probability during atmospheric river days has to be higher than the probability during non-atmospheric river days. And we introduce our only parameter, the only parameter that you can tune in our methodological approach, which is delta. Delta is multiplying the probability during non-atmospheric river days. It can take values from 1 to infinity, and then depending on the value of delta, your attribution is more strict or more relaxed. If you choose a value of delta equal to 1, it's only necessary that this probability is higher, and then you make the attribution. But if you want to be really conservative and you really want to make sure that the probability during atmospheric river days is really, really high compared to the probability during non-atmospheric river days, then you can start increasing the value of delta. And we performed our analysis for each location of our study region. This figure might look a little bit complicated, but let me walk you through it. So first, the size and the shading of the donut chart is indicating the percentage of wet days, or like days with precipitation, that were attributed to atmospheric river conditions. And then the ring is indicating the contribution of each atmospheric river level. Overall, about 30% of the wet days can be attributed to landfall in atmospheric rivers, but there is also a really nice spatial pattern. This time it is not that obvious. It is not following exactly the frequency of atmospheric rivers, but is also following the spatial pattern of wet days and precipitation intensity. We can attribute more precipitation events in the regions where precipitation is more frequent and where precipitation is stronger. And then we tested the sensitivity of this result to our parametrization. We used delta equal to 2 and delta equal to 3, and we found that these results are especially robust over the regions where precipitation is more intense and more frequent. We also compared our results to the ones we get if we change the input data. And although there is a clear difference in the magnitude, the spatial patterns were still consistent. So this takes me to the final part of my presentation, which is step number 2. Now we're going to use nonlinear time series analysis to attribute landslides to the atmospheric river induced precipitation. And for this, we're going to use event coincidence analysis. This is a nonlinear temporal correlation measure. And to give you an intuition of this, of the mathematics behind that, we have two time series I and time series J. In this case, these are precipitation events related to atmospheric rivers. These are landslide days. And you can choose a time window when you consider, like, especially the size of the time window needs to reflect the time that you consider to be coherent with the physical process. After you choose delta t, you start scanning the blue time series, looking for orange events that happened after blue events within this time, this temporal delay. So for example, and we always keep this, we start scanning our time series and we find that, okay, here I have this relation, not only the two events are inside the gray window, but also the blue event is happening before the orange event. And that's how we talk about directionality. And here is also happening the same, but here it is not happening. And in particular, if you can find different events, in this case, different atmospheric rivers within this time frame, then we say that this landslide event was caused by an atmospheric river family. If it is not the case, if we can only find one atmospheric river, then we say that this landslide was caused by a single event. Okay, so how we choose delta t? We use already published result that says that the optimal time window to identify atmospheric river families along Western North America is 5 days. So we chose 5 days, and these are our results. Sorry, before I keep going with the presentation, let me tell you that you can also test the significance of this relation, and to do so, you keep the same number of atmospheric river events, same number of landslide events, but you shuffle them and you simulate a stochastic or like random time series. With this random time series, you again calculate the same correlation, and you can then determine if the value that you're getting is really extreme, and therefore it's due to a strong causal relation and not due to randomness. So we did so, and here we're only showing results that are significant at the 0.05 significance level, which is like a high significance level. This doesn't mean that atmospheric river conditions are not do not precede landslides in the mainland. It means that we were not able to determine the significance of this relation. But along the West Coast, the relation is highly significant, and also the percentage of landslide days that were preceded by atmospheric river precipitation is quite high. In most of the locations, this number is greater than 75%. And if we look at the rings, then you can see that single atmospheric rivers do play a really important role in triggering landslides as well. And finally, if we analyze the contribution of each atmospheric river level, you can see that now the darker colors have taken over the distribution. So we were able to conclude that from 1996 to 2018, atmospheric rivers caused 86% of landslide days in Western North America. And we again tested these to the parameterization. More strict parameterizations yielded basically the same result. Then we used different input data. There are some other significant grid cells, but like the most important grid cells along the Western coast are still showing up. And then we also tested the sensitivity to the temporal domain. This is in particular for 2010 to 2018, where more landslides were reported, and still we have the same spatial pattern, although we started having more landslides here in the mainland, the attribution is not significant. And if we consider the period from 1996 to 2009, there are like really few landslides reported, but still we have this nice spatial pattern. And with that, I want to conclude my talk, and I want to convey my final take-home messages First, we have developed a theoretical framework to quantify the causal relation between atmospheric rivers and precipitation-induced landslides. We can extend our approach to other regions, other atmospheric drivers, and other precipitation-induced disasters. We are really curious about how can we use atmospheric rivers to improve landslide forecasting. And finally, after the California disasters, last Sunday, The Guardian published this headline: atmospheric river storms are getting stronger and deadlier. The race to understand them is on. Thank you.